In this video, I'll be introducing covering maps and how you use them to calculate the fundamental group of the circle. First of all, let's go ahead and provide intuition on what a covering map is. The idea of a covering map is sort of like a stack of pancakes. So you basically have a bunch of different open sets, which are disjoint, that are stacked on top of one another. So each one of these is a different open set, and they're just stacked, one on top of the other, but they are disjoint. Now each one of those open sets gets mapped homeomorphically onto a base open set. So if each one of these is a pancake, and this is a stack of pancakes, you understand that each pancake is separate from each other one, they're disjoint, and that every one of those pancakes is mapped homeomorphically onto this single pancake. But that entire stack of pancakes is different from a single pancake. And so what you get is the idea of a homeomorphism on restriction in the domain. And this is a useful property because it's one step up from a continuous map, but it's also one step down from a homeomorphism. Because it has homeomorphisms in it, but the total map is not a homeomorphism. But it can provide useful information if you want to create a strong propertied map between two spaces that are not homeomorphic, but have related properties. For instance, the circle and the number line, the real numbers. So let's go ahead and give a proper definition for a covering map. So, what is a covering map? Well, we just described it's a continuous map, P, between two spaces x and y. Now we're going to make this a bit more general than the definition I gave. So we're going to say that P is a covering map if for every y, which is an element of y, we have it that there exists some open U, a neighborhood around y, such that it had that property as I described before. And the way we write this out is P inverse of U is equal to a disjoint union for alpha and j of open sets V alpha. So these are all open sets of X, and this is a disjoint union of all of those. Basically meaning the pre-image of the U of the single pancake is the disjoint union of V alpha, each individual, the stack of pancakes. Now we also need to have it that P restricted to V alpha is a homeomorphism, which takes you from V alpha to U. So this is a homeomorphism right there. Each one of these U's is called evenly covered. So if there's an open set whose pre-image is a disjoint union of open sets that map homeomorphically onto U via your covering map, then that open set is called evenly covered. So any one of those single pancakes are evenly covered by the stack of pancakes. So a really basic example of this is something like a projection. So if I have a projection pi 1, which takes you from x cross y down to x, this is the projection onto the first component, and we have it that y is a discrete topological space, it's under the discrete topology, well then every single open set in X is going to be evenly covered by pi 1. And the reason for this is because pi 1 inverse of some open set U is going to be equal to, well, pretty obviously it's going to be U cross Y. But U cross Y is a disjoint union. It's a disjoint union for every single element in Y, U cross the set of that single element. And so, because Y is discrete, we know that each one of those single element sets are in fact open. And so right there you have a disjoint union of open sets, and it's pretty obvious that each one of these is homeomorphically mapped onto U via pi 1. That's our first example. Our second example is much more pertinent to the topic at hand, and it is a covering map from R, the real numbers, into the circle. The way we define it is P of x is equal to e to the 2 pi I x. Or if you want to view S1 not as a subspace of the complex numbers, but rather as pairs of points, this is going to be equal to cosine of 2 pi x sine of 2 pi x. Remember Euler's identity. So what is this map? Well, you might recognize it as a parameterization of the circle. So if we have our number line here, let's go ahead and say this is 0, this is 1, this is 2, this is -1. Well then, the map P, which goes onto the circle, if this is our starting point 1, well then 0, e to the 2 pi I 0 is just 1. So 0 gets mapped to 1. Alright? As you go from 0 and you approach 1, you're going around the circle counterclockwise. And then when you finally reach 1, well then you get e to the 2 pi I. By Euler's identity, that is just 1. And when you go from 1 and you start going to 2, you go around counterclockwise again. And when you finally reach 2, it goes to 1 again. If we were to say start at 0 and go back towards -1, we would be going around clockwise. But then once we finally reach -1, we would have e to the -2 pi I, which is 1 again. And so what you get is that every single integer maps onto 1. Or, in other words, that the pre-image under P of 1 is the integers. Remember this fact. Pin this in your mind. This is an important fact. We will use that later. Now, how do I prove that this is, in fact, a covering map? Well, this definition for a covering map can basically be rephrased as there is an open covering of Y such that all of the open sets in the open covering are evenly covered. And so I can do, for S1, the open even covering of the real part of Z bigger than 0. That's our first set. Then we can have the real part of Z less than 0. That's our second set. Then we can have the imaginary part of Z bigger than 0. That's our third set. And the imaginary part of Z less than 0. That's our last set. And so if we have our circle, the real part of Z bigger than 0 just means all of those which lies on this half of the circle. So it's this open interval, this open arc around the circle. The real part of Z less than 0 is that on this side, that open arc right there. The imaginary part of Z bigger than 0, well, that's just the top half of this circle, like that. And then the imaginary part of Z less than 0 is going to be the bottom half, like that. All right, now the reason why I picked these sets specifically is because of properties of cosine of 2 pi x and sine of 2 pi x. Namely, that on each of these intervals, they are strictly monotonic. So for instance, on this real part of Z is bigger than 0, we know that sine of 2 pi x is strictly monotonic. It's going up that entire time, strictly. And we know that for imaginary part of Z bigger than 0, we can see that cosine is strictly monotonic. It is going up strictly in that entire interval. That's the x value. The x value is increasing strictly that entire time. And so what that can tell you is that it is in fact injective, in that if you pick the right domain, it's going to be surjective, and then you have a bijective function, and then you can prove it's homeomorphic. So how exactly do I prove this is homeomorphic? Well, let's look at real part of Z is bigger than 0. So we just have the positive half of the circle. Let's go ahead and call this U. What is P inverse of U? P inverse of U? Well, we know that 1 is in here, and so we know that this has to contain 0, all of the integers. So if this is our number line, it has to contain all of the integers. So all of these are in the pre-image so far. Well, if we go along that way, right here the angle is pi over 2. or that angle pi over 2 is 2 pi times a quarter. And so that means that all of those values up to a quarter past the integers are included as well, because we want it to go all the way up to there. And then right down here is negative pi over 2, which is the same as 2 pi times negative a quarter. And so that means all the values a quarter less than the integers are also included. And so our intervals are n minus a quarter to n plus a quarter. And this is for every single integer n. So let's go ahead and call this Vn. Now it's pretty obvious that Vn maps bijectively onto U, each one of these Vn's. Now, why do they map homeomorphically? Well, let's go ahead and take Vn bar. Vn bar is the closed interval from n minus a quarter to n plus a quarter. And Vn bar maps onto, and you can prove this, U bar. That's just by properties of continuous maps. What you get is that P restricted to Vn bar is a bijective continuous map from a compact space into a Hausdorff space. And you can prove that any continuous map from a compact space into Hausdorff space is homeomorphic. We can restrict it to just Vn, and then we can get Vn that maps surjectively into U, and because that's a restriction of a homeomorphism, it is a homeomorphism itself. And so we get that P restricted to Vn from Vn to U is a homeomorphism. And then you can do a similar thing for each one of these intervals, because either sine or cosine will be strictly monotonic and thus injective and obviously surjective. Now, a couple properties which are pretty easy to prove, so I won't do them here, of these covering maps is that, well, you can restrict it. So if I have a covering map P, which goes from x to y, and I have some subspace y0, then I can restrict it to P restricted to P inverse at y0, and this will be a covering map from P inverse of y0 into y0. So this is also a covering map. The second property of them is that if I have P from x to y, and I have P prime from x prime to y prime, that means that P cross P prime is a covering map. And that this P cross P prime is going to be from x cross x prime to y cross y prime. All right, those are just some properties of continuous functions, but we've just extended it to covering maps. Now, a very important concept that comes along with covering maps is that of lifting. And we're going to see why lifting is important, specifically when talking about the fundamental group of a circle. So, first of all, what is a lift? So a lift, well, first you have to be given a covering map P from x to y, and you have to be given another map F from some space Z into the codomain Y. Then a lift is going to be some continuous map F tilde, which is from Z into the domain X. And we have it such that P, the covering map, composed F tilde is equal to F. So basically meaning we have this diagram. We have Z, we go via F to Y, we have a covering map that goes from X to Y via P, and then F tilde is the map that goes from Z to X. And F tilde makes this diagram commute, basically meaning that if you do F tilde, then do P, that's the same as doing F. Let's go ahead and apply this to the covering map on the circle. Now, what we will define is some map that we're going to lift via this covering map on the circle. Namely, let's call it omega n. This will be a map that takes you from the interval into the circle. And how you define it is omega n of s is going to be equal to e to the 2 pi I n, this n being from there, s. Now, if n is an integer, this is a loop that starts at 1 on the circle and goes around n times. How do I lift this? Via this map. So remember, In order for it to be a lift, we have to have P of omega n tilde of S has to be equal to omega n of S. And remember what P is equal to. P is equal to e to the 2 pi I x. So that's e to the 2 pi I omega n tilde of S has to be equal to, well, omega n of S is e to the 2 pi I ns. So right there you have omega n of S, and right there you have ns. And the rest of it is e to the 2 pi I. And so that means that omega n tilde of S is ns. And remember, S goes from 0 to 1. So it starts at 0, ends up at 1. What does this mean? So omega n tilde is going to be a path. And it's going to take you from 0, and it's going to move a long time until you reach n. So it's just going to be that linear path that goes from 0 to n. And so that's actually super useful, right? That means that the loop that goes around the circle n times corresponds with the path in the real numbers that takes you from 0 going to n across time. And so that's a direct relation to the number of times you loop around the circle and the distance you go in the real numbers and the integer you end up with. And so this lifting property will totally give us an explanation for what's going on with the fundamental group of the circle. Now let's go ahead and do a theorem. And this theorem basically says that we can generate a unique lifting for any path in any space given a covering map. So let's go ahead and prove it. So say we are given a covering map P, which takes you from X to Y. Then let's also say you're given some Y0, an element of Y, and you're given some X0, an element of X, such that P of X0 is equal to Y0. Now let's go ahead and say you have some path F, which will be from the interval into Y. So we're doing it into Y so that we can lift it. And we have it starting at Y0. Then there exists a unique lift, F tilde, of F, such that F tilde of 0 is X0. So basically, given this choice of X0, you can construct this unique lift of that path that starts at X0. How do we go about proving this? Well, we should probably start with the fact that there are evenly covered open spaces, right? So if we have, say, an open covering UY for Y and Y, this is an open even covering of Y. And we have it that each one of these UYs contains Y and is evenly covered. So these are all of your open neighborhoods around your points that are evenly covered, guaranteed by the definition of a covering map. All right, what do we do with these? There are specific types of spaces that work really, really well with open coverings. Compact spaces. What compact space are we working with here? We're working with the closed interval. So if we go ahead and backpedal with F inverse of each one of these UYs, for Y, an element of Y, then we have an open covering of I. Now you might expect that we take like a finite subcovering, but no, we don't do that. What we instead do is do the Lebesgue number. Now, I don't have a video on the Lebesgue number theorem, but if I find one, you can find it up there in the iCard. So anyway, what the Lebesgue number says is that there exists some number delta bigger than 0, such that any subspace A of the interval such that the diameter of that space is less than delta, which means that the maximum distance between any 2 points in A is less than delta. That means that that subset A has to lie within one of your elements of the open cover. Why exactly is this useful? Well, it means that if I can create a partition of the interval, let's go ahead and say 0 to S1, unioned all the way up until, say, S n minus 1 to 1. So if this is our interval right here, we've just split it up into a bunch of different segments. Right, there's S1, S2, all the way up until Sn minus 1 right there. And so we've just split it up into each of these little segments, and as long as we have it that Si plus 1 minus Si is less than delta, where this delta is the Lebesgue number, if we have that true for each Si and Si plus 1, then that means that each of these sets has a diameter less than delta, which then means that each one of these Si's to Si plus 1's is contained in one of these preimages. So how can I use that? Well, what that means is that if I apply f to both sides here, so that it doesn't become a preimage, we know that f of this interval, Si to Si plus 1, is contained entirely within some evenly covered open set Uy. And so that means that each one of these little sections of the partition are mapped by f completely into an open, evenly covered space. And then we can use the nice properties that come along with it. What specifically do we want to do here? Well, I want to go through this inductively. So let's go ahead and do our base case. We want to define f tilde inductively. Our base case, well, should probably be f tilde of 0. But we know exactly what f tilde of 0 is. It's x0, just from the hypothesis of this theorem. Now let's go ahead and define it inductively from there. Now we can assume that f tilde is defined on the interval from 0 to, say, Si. Now we're going to define it on the interval from Si to Si plus 1. And then inductively, we have it defined on the interval from 0 to Si plus 1. In case you're confused why this is the base case, S0 is 0. The interval from 0 to 0 is just 0, and so we have it defined on that. From the previous statement, I know that f of Si to Si plus 1 is going to be contained in some evenly covered space Uy. But I also know that f tilde of Si is defined, because right there we have a closed interval. And we also need to have it that P of f tilde of Si has to be equal to f of Si. And we know that f of Si is an element of Uy for some evenly covered open set. What does that mean? Well, that means that f tilde of Si is an element of the preimage of Uy, because I just applied P inverse to both sides there. But this preimage is a disjoint union of V alphas. And because this is a disjoint union, that means that this f tilde of Si is an element of one of these V alpha zeros. And this is a unique V alpha zero, where f tilde of Si is inside of. Now I'm going to use this fact to define it. So say we have S, an element of Si to Si plus 1. Then I will define f tilde of S to be equal to P restricted to V alpha naught. Now, what is P restricted to V alpha naught? Well, by the definition of a covering map, it is going to be a homeomorphism. So this is a homeomorphism from V alpha naught onto our Uy. Because it is a homeomorphism, we can take its inverse and have it remain continuous. Then we can compose it with our f, which is also continuous. And so we result in a continuous map right here, and we can apply that to S. And that's how we define f tilde for S in this interval. Now, how do I know that this is the correct thing for the lifting? Well, remember, P composed f tilde has to be equal to f, right? Well, P composed f tilde is going to be equal to P composed P restricted to V alpha inverse. P composed P inverse, that's just the identity, and you're just left with f. And so we have it. You can also check that by the pasting lemma, that this is in fact an extension of this f tilde that we had defined before. Now, to check that this is in fact unique All you have to do is realize that we started with a point, and inductively, we just did exactly what you needed to do. There's no other way you could do this. So if you were to actually go out and prove that this was unique, you would basically just do this process where you start with a lifting and then take the images of these SI to SI plus 1s and seeing that they were equal to these components. Now we've seen how you can construct a unique lifting for paths. Now we're going to do a bit more of an advanced theorem, but we're just going to skip through it really quickly with an intuitive explanation for why it's true. Basically, if we have a covering map, P, which goes from X to Y, and we have some map, F, which takes you from the product of the interval with itself to Y, and we're also going to be given 2 points, x0, y0, and we have it that P of x0 is equal to y0, and we have it that F of 0, 0 is equal to y0. So this is the equivalent of just starting at y0. Then, given all this information, there exists a unique lifting F tilde such that F tilde of 0, 0 is equal to x0. A very similar theorem to the one we proved before. Now, I'm not going to go through this entire proof, I'm just going to very quickly give an explanation. So, you can use the Lebesgue number theorem again on this. Instead of just doing a normal partition of just a single interval, you now need to do a box partition of this box, which is I cross I. And so you go ahead and get your partition of this box, where each one of these boxes have a diameter less than the Lebesgue number. We have our partition right here. Now, what do? Well, we do it inductively as well. We know what this corner part is going to be equal to. It's going to be equal to x0. Then, by the previous theorem, we can define it on these edges right here. This edge, and then this edge. Because, remember, each one of these edges is basically homeomorphic to the closed interval. And so we define the lifting on those edges, and then we continue inductively. Namely, what we do is we start on this one, we go across, and then we come back around there, and keep going. Let's go ahead and say we know what F tilde is on all of these boxes. We want to know what it is in this box. So how do I define it? Well, you can see graphically that this edge and this edge is already defined for it. And that this box, from the fact that we partitioned it via the Lebesgue number theorem, will be mapped into an evenly covered open set. And then basically, if you do the exact same logic we did there, you can find that this entire connected line right here lies in one of those V alpha knots. And then once you have in one of those V alpha knots, you can do the exact same formula and define it on the entire thing. And that's that. And the reason it's unique is basically by the same reason that's unique. Now let's go ahead and give one more theorem regarding these liftings. It's going to be theorem 5. What it says is that if you have two paths, f and g, which go between, say, y0 and y1 in some space y, and you have a covering map p, which goes from x into y. And let's also say you're given a point x0 such that p of x0 is equal to y0. Given all these assumptions, if we have f path homotopic to g, that means that their lifts, f tilde and g tilde, are also path homotopic. What this means is that not only are they homotopic, not only do they have the same starting point, which was just from this theorem, they also have the same ending point. And that's a bit harder to prove. Now, I'm going to very quickly go through why this is the case. So, if you have some homotopy H, a path homotopy, that is a map from I cross I into Y, which is between F and G. Then we can go ahead and construct H tilde by the previous theorem, the lifting of H, which is then a map from I cross I into X. And you can very clearly show that F tilde is mapped to G tilde via this homotopy. Now, to prove that they have the same endpoint is a bit harder, but it's not really hard. You just have to use the fact that this lifting is unique. It's very important that it's unique for that reason. Now that we have all of this set up, what can we do with it? Well, we take these ideas and we create a new definition of a new map. And it's going to be called a lift correspondence. And so basically, what we do is we define a new map, phi, where we pick a base point x0, and this will be a map that will take you from the fundamental group at y, at some base point y0, into p inverse of y0. And we need to have it that p of x0 is y0. And the reason for that is because we want the unique liftings according to this base point x0. So we define phi of x0 of a equivalence class f to just be its lifting, which is unique given this base point x0 at 1. And because of the previous theorem, that if their underlying maps are homotopic, that their lifts are homotopic, that means that the choice of representative for this equivalence class is arbitrary. It'll be the same value no matter what. They will always end at the same point. So that is just the ending point of the lifting path it creates. And so we have a well-defined map. So we're going to use this map, and I think you can see where it's going, to prove the fundamental group of the circle. The fundamental group of the circle at any point x0 is isomorphic to the additive group of the integers. Let's go ahead and first calculate the fundamental group of S1 at the point 1. This is the circle, right there is the point 1. Then we have this map phi. Let's go ahead and pick a base point at 0. So phi, we pick the base point at 0. That will be moving into p inverse of our base point, which is 1. P inverse of 1, if you remember, is just the integers. If you kept that mental tab, here's the payoff. So right there, we have a map which takes in a member of the fundamental group, outputs an element of the integers. Let us just prove that this is an isomorphism, and then we have it. Because remember, S1 is path connected. And because S1 is path connected, all of its fundamental groups are isomorphic. And so if we just prove it for this, we prove it for all of them. So how do I prove that this is an isomorphism? Let's go ahead and first prove that it is a bijection. So why is it surjective? Well, if you remember, we had some maps, omega n. Remember, we had that lifting that started at 0. We had that lifting that started at 0 and went to n. It was the linear map that went between them. And so phi 0 of omega n is going to be equal to, by definition, omega n tilde of 1. And if you remember, it ends at n. And because this type of function can be defined for any such n, you will be able to get out any integer from these. And so phi 0 is surjective, because any integer can come out the other end. And I'm sorry, this should be the equivalence class on omega n. Now, how do I know that it's injective? Well, I have phi 0 of, say, the equivalence class on f is equal to phi 0 of the equivalence class on g. What does that mean? Well, that just means that f tilde of 1 is equal to g tilde of 1. Now, we also know, by the fact that we picked the base point, that f tilde of 0 is equal to g tilde of 0 is just 0. They all have to start at 0. So we get two different paths that both start at 0 and both end at the same point. These are paths in R, in the real numbers, on the real line. R is simply connected. What does that mean? Well, it means that any two paths between the same two points are homotopic. So this means that f tilde is homotopic to g tilde. Well, let's go ahead and say they're homotopic by some homotopy H. Then we can construct the homotopy P composed H, the covering map composed H, which will be a homotopy between F and G, as you can check. And so we get that F is homotopic to G, which means that their equivalence classes are equal to each other. And so we get that if phi of F is equal to phi of G, that F is equal to G. Nice. Now we know that it is surjective and injective. But now, the fact that this is injective means that if I have phi 0 of some F, it has to be equal to some n. But that n is equal to phi 0 of the equivalence class on omega n. Oh, so that means that the class on F is equal to the class on omega n for some n, which means that every single loop in the circle is homotopic to one of those loops that goes around n times. Now let's go ahead and check that this is, in fact, a homomorphism. So let's go ahead and do phi 0 of F star G, right? Now, by this previous fact, that any loop around the circle is just one of these loops that goes around it n times, we know that phi 0 of one of these is just going to be phi 0 of omega n star omega m, just for some n and m. Now this is equal to, by the properties of that star operator, omega n, the equivalence class on omega n star omega m. Now, omega n star omega m, so this means that you would go around n times first, and then you would go around another m times. Well, that's the same as just going around n plus m times. So that is going to be equal to phi 0 of omega n plus m. That is equal to n plus m, which is just equal to phi 0 of the equivalence class on F plus phi 0 of the equivalence class on G. And thus we have a homomorphism that is bijective, and thus it is an isomorphism. So a very quick recap, like the cap of a marker recap. Anyway, we went ahead and defined what a covering map was. We gave a couple good examples, including the very important one from the real numbers to the circle. We defined what a lift was and showed that there exists a unique one given a base point for any path, and that any two paths that are homotopic, their lifts are homotopic as well. And then that was enough information to prove that the fundamental group of the circle is isomorphic to the integers. Now, a very easy proof from here is you can go from the circle to the torus, and you can prove that the fundamental group of the torus is isomorphic to z cross z. Now, I want to see the proof of this in the comments. So if you have a proof of this, go ahead, write it in the comment section below. Anyway, that's it.